Alrighty, in the last video I misspoke just a little bit. I said that we were going to discuss the most powerful concept in geometry. What I should have said is we're going to discuss the most powerful concept in science. And of course, geometry is an integral part of science. So that's why I said that. But at any rate, this is where we've alluded to this concept throughout these videos, but this is where we kind of tie it all together. It's coming to a point here, and that point is what's known as a fractal. Okay, and this is where perhaps all my other ideas are perhaps a little bit quirky and inventive and idiosyncratic, but this is where my ideas may veer into completely radical. It's not radical because it's wrong necessarily, because it's purely logical, and it's actually very simple. It's radical because it's different. I don't think you're going to hear these, you'll hear these ideas, but you won't hear them stated quite this simply and this powerfully anywhere else, because I'm so simple-minded that I don't have a problem seeing the universe as being this simple. So let's just define a fractal. A fractal is iterative self-reference. I hate to have to say that word, iterative. Anyway, an iteration is a loop. It's a recursion. When you're calling when a function calls itself, that's an iterative self-reference. Okay, that's what a fractal is. People see it as geometry, and it is, but it's more of an algorithm. It's a way of generating a kind of logic. Okay. And it goes well beyond geometry, because if you believe that the universe is self-organizing, as I do, if you believe that life is self-organizing, as I do, then you must believe that the universe and life are fractals. Because at the heart of any self-organizing process, there must be this algorithm of iterative self-reference. Now, that's just that's a belief. I think a lot of people believe it. I don't know that a lot of people would state it that strongly, but that's just how things self-organize. Okay, now we recognize the importance of complexity and emergence in modern society and in nature. Okay, those things are just now a given. That's something that modern man has learned and has found useful. Okay. Ancient man didn't have those kinds of concepts available. Okay, so if we recognize the importance of that, then modern man should be using fractal logic at every scale of time and space. Okay, because that's what emergence is. You take something simple, you iterate it, and it generates a complexity. And out of that simplicity emerges things that the simplicity can't hardly even hint at. Okay, what fractals do is they create nonlinear networks of logic. Okay, they don't create lines, they create, well, fields. So, a field is a nonlinear network of logical forces. Okay, so fractals generate fields of logic. That's what they do. Now, one of the greatest mathematicians of all time, John von Neumann, he invented a fractal computer that he called a universal constructor. Okay, now this kind of computer, this is back in the 50s, maybe the 40s, I don't know. Anyway, it's fundamentally different from the kind of computers that we're familiar with. We're familiar with Turing machines that take a linear tape with symbols and it reads it, in a sequential fashion. The universal constructor takes fields of information and iteratively self-references them. And he showed that this could create a digital computer. And these things go by the name of cellular automata. And the most famous cellular automata was invented by a mathematician named John Conway. And he called it the game of life because it simulated a living process. Now, you'll probably recognize that the universe that I invented in previous videos is a cellular automata. It's a spatial computer that self-references iteratively through time. The difference, though, is in von Neumann's telling and in Conway's construction, the grid is a given, okay? And so the information that's animated through that is then biased. The patterns that it creates are biased by the choice of the grid. Well, the grid is like a postulate, and it becomes a homunculus. So you're going to see the patterns that are defined by the grid. So what I did was I took it another layer deeper, and I said what the automata does is first and foremost define the grid. So the universe is perpetually calculating the grid. We don't even talk about what kind of information might be in the grid. We're just going to take it on faith that through the process of iterative self-reference, it will build this fractal information that is defined by the animation of the grid. The grid in the game of life is static and the information is animated. What I'm saying is we need to animate the grid. Okay, we need to, the coordinates themselves are the units of animation and information. So this is consistent with the way I see life creating the molecules of life. It's actually, the molecules are defining the coordinates. So this is basically philosophy. I mean, I'm spouting this DIY homemade philosophy here about fractals, which, nobody is required to believe this or do this, but we logically know that something like this must be done if we're going to logically understand life. So let's go into the geometry. The geometry is this European dude named Mandelbrot in, I don't know, the 50s and 60s. He started talking about this geometry called fractal geometry. And rightfully so, he's the father of fractals. But they were doing fractals, at the turn of the century. This guy named Koch and Sierpinski. This is a simple fractal, and what a fractal is self-same geometry. So you take a geometry, in this case a triangle, and then you make triangles. In this case, we're eliminating triangles from the pattern, and we can do that infinitely. And so everywhere you look in the geometry, you see the same geometry. Now we could do this exact same thing as Sierpinski triangle. We're not limited to 2 dimensions. We could do it in all dimensions. This is a Sierpinski triangle using tetrahedrons. So you can see the difference there. Now, an even simpler, well, I shouldn't say simpler, but an alternative is called a Koch snowflake. And all he does is he takes this triangle and he says, each side can be triangularly divided. So if we take the base one and we go to step 1, and then we do that again to this, and then eventually we're going to have this complex curve that has these mathematical properties. And I pulled this off a website that was demonstrating a way to build a machine, a code. In this case, it's the 3D software I use called Rhino. It has a coding language called Grasshopper. That's what this is written in, and they show how you can wire up this machine, and that code will generate these curves. Now these are just simple cases. If we get into the most famous one, this is called the Mandelbrot set. And the reason it's called a set is because it's just a set of points. It's generated, this is a Cartesian plane, but it's generated from a complex plane. So what you do is you query the complex plane. You just use a simple function, query the plane, it gives you a response. It's either true or false. If it's true, you put a black dot, and if it's false, you just leave it blank, or it's a white dot. So all they're doing is creating a two-dimensional black and white plot of a simple function from the complex plane. Okay, now this curve is infinitely curved. If you zoom in on any of these little curve spaces, what you're going to see is more curve spaces, and if you zoom in on these, you get more curves, and it's just infinite. The higher the resolution, the farther you zoom in, the more self-same curving you see. So it's a fractal curve. Okay. Now this particular curve, the Mandelbrot set, is generated. It's hard to imagine that something so complex can be derived from something so simple. And okay, so this is the equation. It's called a power series. It's the same as a limit in calculus. And the only question you're asking is, will this curve in on itself, or will it diverge? And if it diverges, then I can't remember which is which, but at any rate, all it is z and c, and they're both just complex numbers, so they contain I, the imaginary number. You stick them out on the complex plane. Well, the key to understanding this is, number one, this is you can't even guess that a curve this complex could be the result of such a simple function. Okay, but it is. And so the curve emerges out of simplicity. This complex curve emerges out of this simplicity. Now, the idea is that it's an algorithm, so it's a function. So what happens is you take a variable and you call it x, you plug it into the function, it gives you an output, call it y. Now the next step is to say that x equals y. So we make the input, the output will then be the input, and then we plug it back into the function. So it's a recursive, iterative process. This is an algorithm. If you follow this kind of algorithm, you'll create a fractal pattern. Okay? Well, natural selection is this algorithm. So if you take all life on Earth and then you select from it, then what you've selected then becomes the input for the next iteration. So natural selection. So you say, okay, use A to produce all the life forms on Earth. So all the life forms go out and they sexually produce new life forms and divide and do all that stuff, and that creates B. Well, now the function of B is now select the ones that are able to do this again. So then not everything from B gets to repeat the algorithm, only A does, the ones that we've selected here, and then that gets plugged back into the original function. So it's a simple algorithmic process that creates organisms, selects organisms, uses the selected organisms, create organisms. So this is clearly a fractal algorithm. So what we're going to see is a fractal pattern. We're going to see it everywhere. We're going to see it at the lowest we're going to see it at the highest. It's a fractal process. Okay, so natural selection is a fractal algorithm. Life is generated from this algorithm, so we should see a fractal pattern of life. And of course we do. We see it everywhere. Yeah, you are a fractal. Your first cell is a cellular automaton. The first cell creates two cells. There's self-reference. The two cells self-reference. They create four cells. It's a decompression. Okay, it's a fractal decompression. We keep putting the output. Okay, the instructions aren't in the first cell. Only two cells are in the first cell. Then the instructions for the next iteration is to make four cells. And so it keeps self-referencing. And at the end of the day, you create 37 trillion cells. This is how you can put the information in one cell that generates 37 trillion cells. It's a fractal decompression algorithm. It's the most complex, the most efficient, the most highly optimized decompression algorithm in the entire universe. I mean, it's life, for goodness sakes. So the thing to know about this is that, the universe is a fractal. It's creating, it starts with the base logic. It creates coordinates. Those coordinates create atoms. Those atoms create molecules. Those molecules create, reality, life, and they create the universe. They create the solar systems and the galaxies and on and on and on. It all starts with the same logic. There's a logic that dictates the spatial logic of atoms and the spatial logic of universes, and it therefore must also dictate the spatial logic of life. Now, the thing you got to realize is that this particular curve, the Mandelbrot set, this curve was not invented. Okay, this curve exists whether we find it or not. We discovered it. What we did was we invented a math that helped us discover the curve. Well, these curves are infinite. There's an infinite number of possible curves, and there's an infinite number of possible maths. Okay, we can invent a different math and we can discover different curves. Okay, but logically, there must be a curve for life to discover in order to plot out these atoms in space through time. And so life must invent a math in order to discover it, and that math physically manifests that plot. So these atoms, you, me, the cat, the dog, the amoeba, we are all plots on this curve. This might be human. This might be cat. We're very close on the curve, but we're both plots on that curve. Okay? And life, since the beginning of time, has been trying to plot this curve, this unbelievably complex curve. Now, that's a property of the universe, but in our case, on Earth, it's unique. The actual molecules are unique to Earth. So our language here on Earth, the genetic code, is obviously a fractal language. It has to be able to build these complex structures from simpler properties. Simpler, the camera just went off. So anyway, that's, we could talk about fractals forever, obviously. I mean, they're very important. They're very powerful. They're difficult to comprehend in full, but they're simple to comprehend, in the simplest possible specifics. And that's the way we need to comprehend them if we want to start understanding how this language does these impossible things that it does. It can't do it like that. That's not a fractal. That's not even a code. Okay? We need to think about life in terms of logic. And the best way to do that is in terms of geometry. So we've invented this fractal geometry that creates this fractal universe that will allow us to create fractal life that's going to show us a fractal code. It's just simple logic. So in the next video, we'll take a big picture view of how that might be possible.